Over the years, I've been asked quite a few times which Quencher molecule is the best choice for a TaqMan probe. Excellent question. To answer that, let's look at a couple of different options. Applied Biosystems real-time instruments officially support two different quenchers, the first of which is an oldie but goodie called Tamra Dye. A Tamra Dye has been around for a long time and it's still widely available. Here's an example of a target sequence to which I want to design a probe. And here's the probe. Notice the FAM reporter on the 5' end, and of course Tamra Dye doing the quenching on the 3' end. Now, this probe will work, but just note there are a couple of potential drawbacks to using Tamra Dye as the quencher. The first is that Tamra Dye is itself a fluorescent molecule, and as such, it gives off background signal. That fluorescence has to be accounted for independently, and as such, Tamra Dye will occupy one of your dye slots on a filter-based machine. Not usually a big deal, really, since you still have several filters left. The bigger concern? Tamra Dye quench probes tend to be on the long side, and that's because probes need to have melting temperatures that are, around 70 degrees Celsius. And in order to get there, the probe will often have to be 35 or 40 bases or even longer. And as we'll see in a moment, longer probes are often less specific. Yes, you heard me, less specific than shorter probes. I'll explain that one in a moment. First though, let's look at a slightly newer alternative, namely MGB probes. The 3' molecules on MGB probes actually consists of two subunits. There's the quencher itself, which, unlike Tamra Dye, is non-fluorescent, and so it gives off no background fluorescence. That's a good thing. But then there's also a second subunit called an MGB, or minor groove binder. This molecule serves the purpose of increasing the melting temperature of the probe, allowing us to design shorter and often more specific probes. You can see that if we redesign our probe as an MGB, it's much shorter than the Tamra Dye quench probe. In fact, it's less than half the length. The MGB serves as a molecular clamp, holding our probe and template together tighter. And as I say, higher specificity often follows. Now that probably seems counterintuitive, so let me explain. Say I have a target sequence to which I want to design a probe. Now before I do that, I take the scientifically responsible step of blasting the sequence against all known transcribed sequences for the same organism. The point is to find out if my sequence is unique or not. Unfortunately, what I find is that there is a very similar sequence, perhaps a gene family member, with only two bases differentiating these two sequences. Now, I can go ahead and design a Tamra Dye quench probe, and it'll bind to my target with no problem. But because only 2 out of maybe 35 or so bases are mismatches, the probe will probably bind to that unwanted sequence as well. Not as efficiently perhaps, but I'm still going to get erroneous sequence during PCR. But if I redesign that probe as an MGB, it's of course much shorter, and as a result, those two mismatches are a much higher percentage of the total length. So while the probe still binds perfectly to my target of interest, it has much less affinity for the mismatch sequence. And that makes us very happy. I hope this information has been helpful. Keep sending us your real-time questions. In fact, if you're lucky, we might just choose one of yours for the next Ask TaqMan video.